미국에서 LG SEC 2024를 위해서 세션을 하나 준비를 해주셨는데요. Dr. Bahattin Yildiz라는 님께서 세션을 준비해 주셨습니다. 오늘 발표 제목은요. A Spectrum of Incompleteness in NTT, Improved Trade-offs and Faster Lattice Cryptography-Based Applications. 굉장히 복잡한데요. 어떤 내용이 담겨 있을지 그리고 여러분의 실제 코딩과 개발에 어떻게 도움이 될지 한번 들어보는 시간 갖도록 하겠습니다. 그리고 오늘 세션이 끝난 이후에는 여러분께서 직접 이 박사님께 질문을 드릴 수도 있고요. 만약에 나는 영어로 말하는 게 조금 부끄러운데 하시는 분들은 제가 원래 본업이 통역사이기 때문에 한국어로 질문을 주시면 제가 순차 통역을 제공해 드리도록 하겠습니다. 그럼 바로 박사님 모셔볼까요? Hello.
Thank you for inviting me for this talk. So here in Santa Clara in the Emerging Tech Department, I lead the efforts of the Advanced Security team, and we're basically working on some modern cryptographic protocols, in particular things like post-quantum cryptography and homomorphic encryption, which are very important technologies of the future. And of course, because they are modern cryptographic protocols, the classical approaches sometimes are not efficient enough. So we require some new approaches to deal with some of the issues, some of the things that we actually face while implementing these algorithms. So let me just start then. So as I said, two important technologies that we are actually focusing on. One of them is post-quantum cryptography, which is going to replace the current crypto systems such as RSA and the Diffie-Hellman key exchange because of the advances in quantum computing, making these classical protocols vulnerable to quantum attacks. Homomorphic encryption, on the other hand, is a very exciting technology that offers various use cases because it allows computations on encrypted data. So while post-quantum cryptography gives us enhanced security against all attacks, including quantum computers, homomorphic encryption gives us enhanced privacy because you can actually do operations on the data while it is encrypted. But of course, both these protocols, both these algorithms, have a lot of deep mathematical structures in them, and as such, they require a lot of mathematical computations, which sometimes can be quite expensive. And that's kind of what we are going to be focusing on in today's talk, because the main bottleneck in these algorithms, actually, one of the main bottlenecks in these algorithms is polynomial multiplication in a quotient ring, actually, and to be more precise. So a typical operation that involves polynomial multiplication, or sometimes called convolution in a quotient ring, it happens in a quotient ring of this form, which is basically polynomials of degree at most n, so n coefficients, but the multiplication actually has two very important steps. One is that the coefficients are actually multiplied and added modulo q, and then also there's this polynomial modulus in the denominator, which makes things even more complicated, because when you multiply two polynomial, you will always have to come back to the n coefficients by taking this modulus. And so in these algorithms, we have really polynomials with huge coefficients and very high degrees. And so multiplying these actually becomes very expensive. So there are certain approaches for these polynomial multiplication, how to do this polynomial multiplication. Of course, the first instinct is to use schoolbook algorithm, which basically helps you multiply two polynomials without any structure, just using the regular schoolbook multiplication that we see in high school. But that has O(n) squared complexity. There are certain advanced algorithms such as Thom-Cook algorithm, which has O(n) to the power some logarithmic power, which is better than O(n) squared, certainly. And then there's the Karasup algorithm, which is kind of a special case of the Thom-Cook algorithm with k is equal to 2. And then of course, there's the NTT, which is the number theoretic transform, and that's kind of at the center of my talk today. So NTT actually is among these the most efficient one. It's basically just fast Fourier for integers in a special case. However, it does use some really deep mathematical things such as Chinese remainder theorem for rings and cyclotomic polynomials. So to build the NTT, there's a lot of mathematical background underneath, but for practical implementations, we usually don't need all that. However, the complexity of it is or n log n, which basically beats all of these previous algorithms. So NTT actually plays a very important role in both PQC algorithms and FHE algorithms. For example, in FHE, and by the way, FHE means fully homomorphic encryption, PQC means post-quantum cryptography. In fully homomorphic encryption, NTT makes up to 50 to 80% of the workload, depending on which algorithm is actually being used. And then there's like a snapshot of the NTT workload in some of these recently standardized PQC algorithms. So recently NIST standardized 4 PQC algorithms, 3 of which are signatures, digital signatures, and one is a key exchange mechanism. So the key exchange mechanism is Kyber, and these are the NTT percentages, workload percentages in the key generation, encapsulation, and decapsulation phases, which are the 3 main operations in Kyber. And then we have these 2 lattice-based digital signature schemes, which are Falcon and dilithium. And these are the workload percentages of NTT in key generation, signature generation, and signature verification phases. And so in key generation, Falcon uses something different called fast Fourier sampling on floating arithmetic, so it doesn't use NTT, but in its verification and signature generation, it still uses NTT quite significantly. Now, NTT, if we kind of get into NTT, it has a layered structure, actually, which is kind of going to be important in understanding what we are going to talk today, because usually the cyclotomic in the quotient ring is of the form x to the power 2 to the power k plus 1. So essentially that means 2 to the k is the number of coefficients of the polynomials that we are going to be working with, and that automatically leads to k layers for NTT. In the first layer, we split the polynomial into the quotient into 2 polynomials of smaller degree, 2 to the k minus 1, half the degree basically. And each time you basically add a layer, you halve the degree by 2 and so on, until at the very last step, you basically have now splitting into linear polynomials. And so this gives a kind of a recursive structure for the NTT, and it also gives us a way to kind of play with this layered structure to kind of come up with the optimal solution when implementing it. So this is kind of the description of that layered structure. That's like the first layer. In the first layer, the polynomial is split into 2 polynomials. So the two smaller polynomials have like half the coefficients as the original one. And then each time we halve the coefficients. And then in the end, at the kth layer, at the very last layer, we basically have these coefficients now that are all kind of constants. So we go from polynomials to constants. Instead of multiplying polynomials at the very last stage of NTT, we're basically multiplying just constants. And then we have to, of course, reverse this process to go back. That's called the inverse NTT. So this is how NTT works in this layered structure. Now, of course, when we talk about NTT, we actually usually mean the full NTT, which is a k-layer NTT, and that of course puts some requirements on the modulus Q. In order to have the full NTT, the modulus Q needs to satisfy a mathematical condition, a modulus condition basically, and so when the number of coefficients gets smaller, sometimes other multiplication algorithms can actually be more efficient. This is exactly what happened with Kyber. So what happened was that in Kyber, basically the ring that we are working on it has this coefficient 256, has degree 256. So a full NTT layer has 8 layers basically, and according to the previous condition, that requires that the prime modulus needs to be 1 modulo 512. So that automatically gives us restrictions on what Q can be, and since we want operations to be kind of efficient, we want a smaller Q, but the smallest such Q turns out to be 7,681. This was the one that they used in their original submission. But then they actually noticed that if instead of going full NTT, they stop at this layer 7 and just use schoolbook on those last polynomials, which are basically now linear polynomials or degree 1 polynomials. This way, they would change the requirement for the prime modulus to be 1 modulo 256. But then this gives us more primes to choose from, and then they chose 3,329 for security concerns. And choosing the smaller prime and ending at the previous layer, or at the smaller layer, actually ended up making the implementation much more efficient. And so basically that's what we kind of did. So we basically wanted to systematize this. And so in order to systematize this kind of thing, we wanted to know if there's a threshold after which other multiplication algorithms become actually, or a threshold for which that determines when the multiplication algorithms such as Karasuba or Schoolbook can be actually more efficient than NTT. So for example, this is one of the things that we did, where we took Q to be 3329. That's the prime modulus that was used for Kuiper, and we see that there is this kind of threshold for the number of coefficients where we have when the polynomials are below that threshold, the number of coefficients is below that threshold. Karasuba and Schoolbook multiplication seem to be actually performing better than NTT in terms of the number of cycles that are required to do the multiplication. And so that was kind of the extreme case that happened with Kuiper, because in the Kuiper they stopped at the 7th layer, which means the polynomials now had two coefficients, but the threshold shows us that we might have even more coefficients while still the other multiplication algorithms beating NTT. And so we did this experiments for different primes. This is the original prime that was used by Kuiper, and this is just another prime that we can actually play with. So of course, with bigger primes, the thresholds kind of moves towards the right. So these results basically show us that we can apply NTT up to a layer such that the number of coefficients drops below this threshold. And at that time, instead of using the full NTT, the Schoolbook and Karasuba can actually be applied. So that will kind of give us a more efficient implementation that involves kind of a hybrid approach where we use some levels of NTT and then some of these other well-known multiplication algorithms. So we defined this thing. We wanted to systematize this thing. So we made this into a definition. We called this an incomplete entity, which we also gave this parameters, LK layer incomplete entity. So LK layer incomplete entity means that instead of the full K layers, we actually apply only L of them. We go up to the L layers of NTT, and then we apply the other multiplication algorithm. So at the L layer, the polynomial is going to have these coefficients of 2 to the power k minus L. So basically, as L increases, the degree of the polynomials is going to decrease, the number of coefficients is going to decrease, and so we will have, at some point, we will hit that threshold that will make the choice of other multiplication algorithms more efficient for us. So LK layer completeness, of course, corresponds to K minus L incompleteness in this case, because we are not doing those K minus L additional layers of NTT that is required to fully do it. And so we kind of come up with this new polynomial multiplication algorithm where we take two two polynomials to multiply, and we apply the entity for those two polynomials, the LK entity, so up to L layers. And then for the remaining, we use some base multiplication, which could be school book or Karasuba. And then we calculate the result of that, and then we apply the inverse entity with, again, these incomplete, the L layer inverse entity to the result, and we end up with the original the product of these two polynomials, or the convolution of these two polynomials. So when we actually kind of can actually say when incompleteness is better, incompleteness is going to be better if the savings from this process actually exceeds the cost of the base multiplication. And in fact, we actually found the exact mathematical function that gives us when the incompleteness is better. And I'm going to explain that in a few slides. But before going to that main picture of what we have actually accomplished in systematizing this, I would just like to talk a little bit about these relaxation on moduli, because what we saw before is that complete entity imposes restrictions on the choice for the moduli. However, if we are able to stop at the different layers of entity, we can actually ease these constraints, and consequently, we will end up with many different prime modulus options that we can actually use. And so we actually kind of systematize this. We actually put this in mathematical terms. We proved a few lemmas, which resulted in the following theorem, where we have two sets of moduli that support L1 and L2 layer entities, where L1 is less than L2. Then we know for sure that as you decrease the number of layers, the set of the prime modulus that are available actually grows. And so we have this really nice relationship between the layer at which to stop and the number of the set of prime modulus that are available to use. So this is actually the main thing that I wanted to talk about today. So this is kind of the crust of the talk here. So we actually turned this whole thing, this incomplete entity, into a function of optimization. So we are trying to optimize something, and I'd like to talk a little bit about this one. On the left, we have like some cryptographic application, and we put in FHE and PQC as examples of applications. But of course, these could be some other cryptographic algorithms as well. But because our focus is mainly on FHE and PQC, that's what we kind of wanted to put in. And so these applications are targeted on some device. Let's say maybe it's a resource constraint device, maybe it's not, but here we're just considering like a device. Now, there are some inputs that we are going to get from this target device. So one of them is going to be the modular addition cost, because those are going to be there are going to be mainly two operations in NTT and school book multiplication. In all these polynomial multiplications, there will be two main operations. One is addition and one is multiplication. And so the modular addition cost, assuming that it's alpha, modular multiplication cost, assuming that it's mu. And then we have two additional parameters. One is the number of coefficients on which that we are going to work with. For example, in Kyber, that was 256. And then we have like security strength, lambda. So the security strength is important because that's one of the things that is going to be affected by the choice of moduli. So the modulus choice will actually affect the security level as well. So these are the inputs. And what we propose is we can actually output an optimal L and an optimal modulus so that all these things are actually, all the security is achieved and the workload of the polynomial multiplication is minimized. And that to minimize that function, we actually have this really nice mathematical formula. So we turn this incomplete entity into a function of optimization, an optimization function where we have the input, where we have a mathematical function that depends on these parameters L, Q, alpha, mu, and as a result, we are actually going to come up with an optimal level of incompleteness or layers, the layered of entity that we need to go with, and the prime modulus. So we just have some kind of numerical results about this. So what we did was we did incomplete and complete. We actually compared incomplete and complete entity for the ring sizes, for different ring sizes. As you can see, for example, in some cases, we can actually achieve almost 40% gain by different choice of L and Q. And we did this for a different number of coefficients. N is 512, N is 1024. In each case, we actually were able to get some improvements on the actual entity, which is usually denoted at the zero as the zero level here. And so what we ended up with, we actually applied this on the actual Kuiper, and we found out that the 6/8 layer incomplete entity-based polynomial multiplication is actually 5% faster than the one that was done in the current Kuiper specification. The yellow line here actually shows the 6/8 layer, which shows that it's actually performs better than the 7/8 layer incomplete entity. So there are a few other kind of utilities of this approach, because incomplete entity does not just or this relaxation of moduli, for example, does not just affect the performance. It also affects the different parameters of different aspects of Kuiper, such as the DFR, optimized DFR, and ciphertext sizes. I mean, I don't have a lot of time to go into the detail of these, but the DFR stands for the decryption failure rate. It's an important parameter in Kuiper, because if you have a high decryption failure rate, it actually affects the implementation of Kuiper. A smaller decryption failure rate is better, and in fact, the Kuiper team has proposed certain thresholds of DFRs that are deemed acceptable. Ciphertext size is also important for Kuiper, especially when it's implemented on resource-constrained devices with limited memory. So basically, I'm just going to kind of go over some of these more quickly. So there are compression parameters that are compression parameters that are used in Kuiper. Of course, we want to lower these compression parameters, but that increases the DFR. And so this basically shows what the kind of DFRs are, DFR decryption failure rate. These two dotted lines here, the horizontal lines, are actually some of the threshold DFRs that were described, that were proposed by Kuiper, and this kind of shows which primes, when we use which prime, what DFRs we actually get for given compression parameters. Basically, when we apply the incomplete entity, we actually get lower DFRs, sometimes much lower, like to the power minus 240, or shorter ciphertext, which sometimes can be as much as 8% compression. And then we can also propose new parameters that give us much better performance parameters than the current ones that we have for Kuiper. So here, this is kind of a picture that shows that we have these incomplete short layered entities, and in each case we see a drop below, and a drop below, when a dot actually goes below, that's a very good thing, because that means we are actually performing much better than the original Kuiper in terms of the DFR. And then, of course, that also sometimes allows compression on the ciphertext size. So there are other kind of utilities for Kuiper. Sometimes some protocols require, for example, their polynomials to be invertible. And of course, to be invertible in a polynomial quotient ring, we need the polynomial should not have any common factor with the quotient polynomial. And so, because NTT splits a polynomial ring into many factors, for each new layer, we actually have a smaller probability of being invertible. And so, fewer of the polynomials in the ring will remain invertible, and such. So, because of this probability of polynomial invertibility actually being decreased, sometimes this means that we cannot actually use complete entity for certain schemes, and some of these schemes are, for example, these BDL-OP commitment, where polynomial invertibility is used to establish binding and hiding properties of the protocol. Some zero-knowledge proofs, the soundness property of the proof actually requires the challenge to be invertible. And to make the dilithium digital signature scheme information theoretically hard, meaning that it's secure in the quantum random oracle model, it needs to have lossy keys, and polynomial invertibility for this is required. In these cases, we cannot actually use complete entity. So what I'm trying to say here is that for the protocols that we are using it mostly for PQC and FHE, this incomplete entity gives us a function of optimizing the polynomial multiplication and finding the optimal values of L and Q. But there are some other cryptographic algorithms for which the complete entity cannot actually even be applied, in which case we are going to be forced to use this incomplete approach and try to come up with the more optimal way to implement these algorithms using our ideas. So in conclusion, what we have done is that we have systematized the concept of incompleteness for NTT. We have turned it into a function, basically, of optimization. This gives us flexibility to, leverage different computational requirements based on the devices, based on the costs. It also allows a diverse set of prime modulus selection. This is also important both in terms of security and in terms of performance optimization. And because NTT is central in almost all the modern cryptographic protocols, this approach actually has an impact on how these cryptographic protocols are going to be implemented. We might be able to provide a guidance based on the costs, based on the target device. We might be able to give a guidance on what kind of level of what layers of MTT needs to be used to optimize the performance and sometimes the memory use. All right, I think that's all I had. I was using a timer. I have 2.5 minutes, I guess, to go with the questions. Thank you for your attention.
2.5 minutes. Yes. Thank you for respecting the time. And we have a crowd here who was paying great attention to your great presentation. 네. Thank you once again. I have some questions. 혹시 질문 있으신 분 말씀해 주시면은 저희가 마이크 전달 드리도록 하겠습니다. 직접 영어로 질문 주셔도 좋고요. 아니면 저를 통해서 통역을 통해서 질문을 하셔도 좋습니다. 혹시 질문하실 분 계실까요? 물론 여기 많은 분들이 계시기 때문에 좀 부끄러우실 수도 있겠지만 날이면 날마다 오는 기회가 아니고 또 바다 건너 캘리포니아에 계시기 때문에 이 기회를 용기 내셔서 한번 활용해 주시면 좋을 것 같습니다. 질문 있으신 분? 손 드신 건가요? 여성분? 아닌가요? 네, 질문 있으신가요? 왠지 질문하실 것 같은데 질문 있으실까요? 질문? 네, 감사합니다. 네, 이렇게 원래 back and forth 왔다 갔다 해야 더 깊이 있는 세션이 되니까 너무 감사합니다. 한국어로 하시겠어요? 아니면 영어로 직접 하시겠어요?
영어로 할게요.
네.
Hi, Bahattin. Thank you for your presentation.
Oh.
Yeah, I'm Jeremy.
Hi.
Could you explain where do you want to
Yes.
apply this
I know that face.
incomplete entity? I mean, you have to explain more about FHE or PQC in general.
Could you repeat the question?
So I think you are too technical today. So could you explain more about the applications, PQC and FHE, what they are, and what are you planning to apply this technology to the PQC
Yes,
and
yes.
FHE?
So I mean, I didn't, of course, have enough time or kind of scope to actually go into the details of what PQC and FHE are. PQC, of course, being post-quantum cryptography, it basically refers to a number of algorithms that have been developed in the last maybe 10 years that are considered key exchange mechanisms or digital signatures for authentication that will be quantum resistant. And for this purpose, NIST in the United States, National Institute of Standards and Technologies, has been running a competition since 2016. And among the many algorithms that were submitted, NIST has actually standardized, finalized four algorithms, three of which are digital signature and one is a key exchange mechanism. And it's also running a fourth round for key exchange mechanisms and another round for digital signatures. One of the key common things about these algorithms is, except for one, the three algorithms that were actually finalized are so-called lattice-based schemes. They depend on the hardness of problems such as learning with error or ring learning with error. In fact, more precisely, they are module learning with error, which means basically we're working with polynomials and in all the key exchange mechanisms, as well as the digital signature for key generation, signature generation, and signature verification. Polynomial multiplication in a lattice or in a quotient ring, in a polynomial ring, becomes a central operation, and it also becomes one of the kind of computational bottlenecks because it takes a lot of resource and time to actually do those calculations. And so basically what we tried to do, we have been basically working to come up with some kind of algorithmic approach to optimize these algorithms, these operations, so they can be implemented in devices. And so that has been our kind of main approach in incomplete entity, has kind of given us a systematic way to approach this problem and to try to come up with like a guidance for choosing the most optimal layer of entity based on the target device and requirements. And of course, a similar thing is happening in FHE. Now, whereas some percentage of the algorithms in PQC are lattice-based, all the known algorithms in FHE are actually lattice-based. They are all kind of similar to what happens in Kyber. Basically, in all of them, the main operations are, again, polynomial multiplication in a quotient ring. Of course, in FHE, we have some more operations, such as like bootstrapping, but even they actually use essentially, they also use polynomial multiplication and polynomial addition and such operations. And because the encryption and decryption basically in these cases is done usually using polynomials, this concept of optimizing polynomial multiplication again becomes of central importance for these algorithms as well. And so that's basically what we have been doing. We have actually showcased some of the applications of incomplete entity for PQC algorithms. so far, but our next kind of goal is to actually show how we can leverage this for optimizing FHE algorithms as well.
Okay.
Thank you so much. 이상으로 질의응답까지 모두 마무리가 되었습니다. 발표가 워낙에 테크니컬했기 때문에 PQC 그리고 FHE에 대한 좀 개념과 응용처에 대해서 설명을 해달라고 질문을 해주셨는데요. PQC가 탄생하게 된 배경, 뭐 4개 중에 어떤 알고리즘이 선택이 되고 성격이 어떤지 또 완전 동형 암호화에 대한 기본 내용들, 히스토리들에 대해서 잘 요약적으로 답변을 해주신 것 같습니다. 9시 40분이 원래 기존의 종료 시각이었기 때문에 딱 맞춰서 끝내주셨고요. 이제 보내드릴까요? Dr. Yildiz, thank you so much for your presentation.
Yeah, thank you. Thank you for having me.
Yes, have a great, wonderful evening. I'll see you next time.
Yeah, thanks. Bye, everyone.
네, 박수 한번 드릴까요? 박수 소리 아마 들리실 겁니다. 네, 이렇게 2일차 오전을 멋지게 장식을 해주셨는데요. 함께 해주신 여러분 진심으로 감사드리고 약 한 8분 정도 쉬고 9시 50분에 계속해서 테크 세션 이어가도록 하겠습니다. 감사합니다.